It was a cold and dark midterm season. Business wasn't good. The Sicilian found out that I didn't properly test my cartel software. So I was demoted to a courier. I was to bring the Platinum Walkman to someone they referred to only as Monsieur Maison. However, soon I discovered this job wouldn't be so simple. Because Monsieur Maison was not the only one after the Platinum Walkman. And it wasn't long until I allowed it to fall into the wrong hands. Hello, hello. You should be able to hear me now. Alright, very cool. I'm gonna get the video working now. I don't want to echo myself too much here, so I have to cut that audio. Alright, so today we'll be working in this GitHub project. I'll send you guys the link, and what we're working on is making a debugger that's testing how our code is running, runtime efficiency, that kind of stuff. That's what the survey came out and said was the most, least taught thing. So we're taking a break from new content now. We did LinkedList a while ago, and that's what we're going to be focusing on, debugging. And now we're just going to create a debugger and like a speed tester for this. It's going to be the exact kind of thing you want to do for your assignment, basically exactly in line with the assignment requirements. You just have to make basically one of these to ensure you do well. So to start this off, I'm going to ask everybody to clone the GitHub repository, the link for which is in the chat there. I'm doing it on this fresh install of Windows, so give it a second. But it'll be ready, and you can all let me know when you're finished cloning it. Come on, paste. Oh, it doesn't paste into my virtual machine. Nice. Bidirectional, no. Now I can copy this over and paste it. Yeah, let me know in the chat if you guys have any trouble cloning it. Just like this. Git clone our project, and then we should be good to go. If anybody of you have trouble with that, let me know, and I can see about helping you out. How do I clone in IntelliJ again? Cloning is really simple in IntelliJ. See at the top, if you have it in this window, there's VCS. Click on VCS, then get from version control, and then you just paste your link and click clone. All done. For me, it won't work because I already have it, but if you don't have it, it'll clone properly. Let me know when you guys are done with that. Maybe I'll launch the poll for that if it allows me to. No, it doesn't let me launch a poll because I'm monitoring it on a different device. But yeah, I'll get started soon. But first, I'll let you know the structure of what we're doing. So here we've got all these classes like before, but now I've got list of links tester, and that is what we're going to be working in all day. That's what we need. That's what we want. That's what we're working in all day. And let me just download a JDK. It's going to take its time. Again, fresh install of Windows on this computer, so it needs its time to install everything. Taking its sweet time, isn't it? Indexing, installing, okay. Well, let me know when you guys are ready. I'll give it like a little bit while I explain what we're doing. So a few tutorials ago, we made this class, a list of links. It's a linked list, a generic linked list. I don't know if you've ever seen a generic linked list anywhere else in this course. I'm sure it wouldn't be important for any of your assignments at all. It's not like it's the main thing of assignment 2 or anything. So yeah, they're very relevant. We like linked lists that are generic. We wrote this in a previous tutorial. So if you want to go back and look at that, if you missed that, you can go back to there. What we're doing today doesn't require you to know what's up with this. It's just this is what we were working with before. And in here, we're going to test, not in here. In here, we're going to test all the functions of that. And then we're also going to test how fast they work. So before we do that, is everybody ready to go? Has everybody got the thing cloned? If you don't have it cloned, send it to the chat. Otherwise, I'll assume everybody has cloned it. Cool. We'll wait a sec then for it to get cloned to everyone. If you just joined, this is we're cloning a GitHub project to be able to code along. So I'll send the link once again. Just like that. And into clone in IntelliJ, you go VCS and then get from version control, and then you paste your link. All good. And then you click clone. Easy peasy. No problem there. So yeah, we'll be ready to go shortly, hopefully. Okay, sweet. So in here, we've got our tester code. So how are we going to test this? Well, first, let's figure out what we're testing. We're going to be testing the list of links class. So I could say list of links, and let's fill it with string is equal to new list of links. Sure. right? And now we can, oh, I forgot to give it a name. We're going to call it tested, right? And now we could do a simple test, right? We could say like list of links, or I don't know, system dot out dot println tested, because we have a toString, right? And we can see if it's in fact empty. We can add something. Let's say tested.add. Ooh, let's say test, and then print, and that could work, right? But it'll only debug like very simple things, and it won't tell us about anything about how it's really running. It'll just tell us the basics of it, and then who knows, maybe it won't even work because it's probably still pretty broken. But this is like the most basic form of testing. It's just to try things out and run methods. So here we can see that when with the empty linked list, it's empty. When it's not empty, right? It's simple. But does anybody have any idea how we can take this further and maybe make this procedure a little bit more rigorous? All right, I'll take your silence as a no. Well, if we want to make this procedure more rigorous, we want to be able to test cases that are weird. So we want to get ourselves into situations where we think our code is probably going to break. And so how do we know when our code is going to break? Well, let's look at our list of links. What are the sort of base cases here? What are the cases that we may or may not be accounting for in this class? Well, the cases we may not be accounting for would be things like adding something to the start of the list, adding something from the end of the list, removing something from the start of the list, that kind of stuff. So let's see, what do we have here? We've got methods for remove last, this kind of stuff, a lot of them. But we should now be able to see that because our methods work with things like looping through the list and like traversing through, we want to test if it works at the start or the end. So if we add a bunch of stuff like tested dot add test2, keep adding to it, tested dot add test3, and now we have more in our list. We can remove stuff, so we can do tested dot remove last and see if this works. But this is still not a great process. We should have some kind of way where we can create our data set and kind of optimize it, make sure it works properly. You can see it's still working fine, but it's not very robust. Well, if we want it to be really robust, what we could do is we could actually have a sort of data set generator, right? We can generate a kind of data set programmatically, so we don't need to do this every time. So in this situation, I'm thinking, well, if instead of, well, we can keep using strings, right? We can say, public static void fill list int number of things list of links. I'll make it a string list, and now here we can say for I equals 0, I is less than number of things I++, we can go through and we can fill the list programmatically. And this is just so that we don't have to do a manual fill every time. And we can see how our list works with really big data sets. So let's say we'll just say a list.add test plus I. Now our list is going to have all these unique strings in it, which are created by the fill list method. So now if we say fill list, or let's say 15 list, or we call it tested. Now it's going to fill the list with 15 things, and we can see if filling it a lot works. It probably will work because it's just doing the same thing over and over again, but it's also good to test this and show that we can programmatically do things. So here we can say system.println tested before and after. And again, this is a bad solution, but this solution is so that we can just see kind of the basics of programmatically testing stuff. So now, yeah, we added a bunch. There is 0 through 14. That's exactly what we expect. Our list is filling correctly. But what if, for instance, we wanted to see how fast this was going? Or perhaps we want to see, is our add method O of 1? Is it O of n? This sort of question. Now, this is where the fun stuff begins. So if we were to say, instead of just filling the list using that, and we instead filled it programmatically, if we said for int I equals 0, let's say I is less than 100, I++, yeah, we can say fill list, I, let's say I plus 5, or I plus 1, so it's not 0 ever, and tested. And then we can say tested equals a new list of links, just so it's empty at the end of every time. And now, well, this won't tell us anything about the runtime efficiency, right? So to make this useful, let's actually store how long it takes to run this method. Now, there's a trick to figure out how long a method takes to run. It's that you can actually figure out the exact time from your computer. So what you do is you type, let's say, long start time equals system.nanotime. And now here, afterwards, we can put long end time equals system.nanotime. Right? And now we're taking the time before and after. And now if we say, perhaps system.out.println end time minus start time, we have how much time it took for the method to run. And I'm just going to say I times 15 so we can really be sure that it's going big. And now, if we run this code, it's showing us how many nanoseconds it takes to add something to our list as our list size increases. And now if you see these numbers, it doesn't make too much sense, but we can actually get a lot from these numbers. It's quite useful because it's showing us the trend of how long things take. And this is useful because it shows us like which big O notation speed it's roughly running at. But you can see that because big O notation isn't a hard and fast rule, it's not like a mathematical theorem for how fast things run, but rather it's more like an expectation. There's a lot of spikes and stuff in this. Like you can see it takes randomly when you have like a small number of items, it's taking a super long time. Here it's taking a super long time. Well, the reason for that, among other things, is that Java is not the only thing running on your computer. You have a lot of things running. So if you look at your task manager, you can see that Java is just one of the many things that's running on here. And Java might not always have the highest priority. Your application might not always have the highest priority. So your computer might be doing other things while it's taking longer for this. And that's why there's spikes in this data. But overall, if you just look at the general trend, you can see that our add method, it's probably O of n, something on there, because it's not like instantly going to a few million nanoseconds, but it's also kind of gradually raising. Does that make sense to everyone? Do you kind of understand how that would work? So again, what we're doing is we're taking a for loop, which increases the number of things that we are putting into our linked list. We are filling the list with that number of things. So here it will start at one thing, then it goes to 16 things, then it goes to 31 things. Like it keeps going up by 30. In fact, if we put breakpoints on here, we can see roughly how many items are being added each time. The Sicilian list of links tester. Caused by class not found exception. May, are you in Eclipse or are you in IntelliJ? Okay, that's probably your issue. I haven't actually tested this with IntelliJ, sorry, or with Eclipse. Sorry, I just haven't had Eclipse installed. I just reset my computer so that it wouldn't crash anymore, and I don't even have Eclipse. So hard for me to say that. A good solution could be just to create a new Eclipse project and drag in all the .java files. I know it's a bad solution, but it's the best I could come up with really quickly, and I'll make sure to update the GitHub repository to work properly on Eclipse for the recorded version. Yeah, but for now, if you have IntelliJ, you can try that. Otherwise, you can drag all the .java files into like the Eclipse in a fresh project. But yeah, you can see here the number of things that the list is being filled with is increasing every single time by a certain amount. Here it's 5 times 15 plus 1, so it's a big number. The list is pretty long. It's got like 76 size. And that's why it's taking an increasingly long time. And if we run it, again, we see that it's probably working in O of n. And that's the general algorithm for figuring out how long something takes to run and its runtime efficiency. You take the start time directly before the method is called, you take the end time directly after the method is called, and you iterate through and increase the size of your data set in order to kind of, because runtime efficiency is a plot of how long it takes versus how many things are in the data set. So as the number of things in the data set increases, you expect the amount of time that it takes to increase or stay the same depending on which big O notation you have. A good way I can show you this is to look at a tester I made for a previous assignment, which I'll have to switch my screen share to another computer. Give me a second, I'll open it. And that'll show you the actual graph of this running on a different bit of code. I'll just quickly show it to you, and then we can kind of try to replicate the same thing with our list of links. While I wait for that to open, I'm going to show you testing for something else. So let's say, hypothetically, you want to test all the different methods of your linked list to make sure it works really well. Well, we got to think of situations where we are convinced our linked list will probably not work. So let's try this. Let's create a new method. We're going to call it, private boolean. A boolean is usually a good method like type for a test because it lets you know if you passed or failed. Like you can just return true if it passes. Private boolean. Let's say test remove from empty. because this is a situation where we wanted to handle it in a particular way, right? So private static boolean, that is. And now we can say if, or wait, let's create our thing first. So list of links, string list. I'm just using string arbitrarily, equals new list of links. Now we can say list.remove last. We can just see what this does. We don't want it to throw exceptions. We just want it to do nothing, right? So now we're going to try this. And now catch exception E. And now here we return false. And now also a good thing to do when you're debugging is to do e.print stack trace. Now what this does is it actually, remember when you run your code and it has an exception, how it has like all the red text that comes up where you're running, print stack trace is what causes that to come up. So we're saying that we're going to try to remove something from an empty list, which is just one of the many cases you might want to test. And then if there's an exception, we'll print the stack trace, that is putting the error up in the terminal, and then saying we failed the test. And here we can say if list dot is empty and list dot or size equals 0, return true, else return false. And what we're saying here is that, if we correctly kept these fields as the way they should be, we can pass the test, else we fail the test. The reason we do this is we want to test for collateral damage, as in we want to see if we're making the common mistake of updating the list size when it doesn't actually change. So we can say, does the list size change out of sync with what's in the list? Now, the reason I'm testing this is, again, I'm thinking about what's going to break our code. The reason I think this will break our code is our remove method, right? It modifies the list and it reduces its size. But theoretically speaking, right? Let's say that it can't modify the list because you can't remove something from an empty list. So it tries to remove from an empty list. That does nothing, but our size might still go down to -1. And that's going to cause a major error because if somebody, let's say somebody's evil and is grading your assignment and wants to test if your code is really solid, what they could do is they could say, the first thing they do when they create your linked list is they're going to create it and then they're going to remove from it. And then your size might go down to -1. And then every time you use your linked list from there on, it's going to have a size 1 less than it should, if that makes sense to everyone. So that's one of the core things you could be testing for. And that is why I've set it up like this. It's just one of the many things you have to think of these sort of as you go. And this one is just one I thought of off the top of my head. So now if we run this, and we call this method first. So let's first call our tester. Let's say system dot out dot println or test remove from empty, and we'll see if we pass the test or not. And then it's going to show us the runtime efficiency. And running it, and actually look, it turns out it was bad. We couldn't remove from it. It's so this method was already bad, and we've already found our first exception. And that is, well, one of the great advantages of debugging. This turns out to have been something that will cause an error. So if we go into here, we'll be able to see what's going on. And it's already good. This error is kind of what we expected. We designed it to throw this error. And if your assignment specifies you should do this, then by all means, you should. The way I wrote this linked list when I was doing the demonstration, I did specify this. However, if you're writing this linked list and your teacher does not ask you to throw this kind of exception, we could not. So let's just think about the case if we don't throw this exception. Here, what we could say instead would be if... Well, actually, this is not even being thrown from their place. So in remove remove from index, or remove last, we can say if this dot size is 0, do nothing, return. And now I think that might still be broken, because notice how this get node index size -2, set next null. Yeah, that might be a bad method. So let's try it again. We'll try the remove last, and we'll see if this continues to cause us errors. Now, it doesn't look to explicitly cause us errors, and it looks to be returning properly. But if we want to be really sure, we know this method had problems before. We can put breakpoints on it, like I showed in a lot of the pre-recorded videos in last tutorial. And this will let us see exactly what's going on in this situation. So we're going this.size is 0. All right, we go next, and we're returning. Perfect. But now, because we do -2 here on size, we might actually want to, we might want to be led into the fact that we might also want to test removing last from a list of size 1. So let's try that as well. We'll make a new little method. The only reason I put these in separate methods is so that you can see which test exactly fails. So let's call this one test remove from size 1. All right, and now we'll say try list of links, and now we'll say just one difference. We'll say what did I call my method here? My static one, fill list or one list. We'll put one thing into our list. The reason I do it like this is just because I already created this method. And now we can remove last, and we can see if the size is 0. Yeah, we need the size to be 0, so that's all good. And this method is mostly reusable, so now we can just do system.println this plus, and now we do our next test, which will be remove from size 1. Now let's run this, and let's see if this test passes properly. Oh, look, it doesn't. So we found yet another error in our linked list. Here, we've got the size is -1. That makes sense, because we are... we're throwing our null pointer exception here because index -1, and the reason we're throwing this array out of bounds exception is that well, if we look at the way our method is implemented, it subtracts 2 from our size. So now if we run this with a debugger, we can see exactly what it's doing. It's saying the size is 0. Ooh, that's a problem as well. The head is null. Oh, this is because it's the first time it's running. Never mind, we're good. Now the size is 1. It's got test 0 in the list, but now size returns 1. Size minus 2 is -1. So this method is inherently, well, it's inherently bad. Right? So instead, we probably want to say this dot size minus 1 is null. Or no, minus 2 is null makes sense, right? Because if size is 2, it's, yeah, that makes sense. We know, remember why we did this. We did this because we want to set the pointer of the node before the last one, like before the one we're removing, to null. But I feel like that's probably a bad solution because, again, it gives us -1 here. So we could say if list.size, oh yes, this dot size is 1, then we could say this dot head equals null. So now we're able to remove from this list. And remember, this linked list is implemented in such a way that head is allowed to be null, whereas the other one is not. So now if we run a tester on this, okay, list.head is null, and oh, but we still call this method, so we should probably put this in an else block. Again, very helpful to use the breakpoint debugger. And the reason we found this mistake is we made this tester. And we can see how making one of the testers, like one of the test methods, led us into seeing that there's a bad method, and then that led us to generate more tests. Now the size is 1, now the size is 0, perfect. So it looks to me like both tests passed. Nice, right? Hopefully that makes sense to everybody. Does everybody follow along how I came up with this debugging process? Great. So again, I'll just quickly go over. Sorry, can you repeat? Yeah, by all means, here. So I'll go through it again. I'll just quickly run over everything, and I'll go back to this shortly. So what I did was I came up with an idea. I said, what happens if we remove from our linked list when the length is 0? The reason I came up with that is because a lot of students have trouble with these kind of methods when the size is 0. If they add null, let's say, or they add something invalid, or if they remove from size 0, sometimes they change the size of the list without actually without changing the data, or they might change the data without changing the size. So here what I'm trying to test for is the size changed appropriately when the data doesn't actually change? And it turns out I did it badly, I did it wrong, so I needed to fix it. And this list is what told me that, like this test is what told me that. So that's why I came up with this test. This test failing led me to put breakpoints on this method, understand why it was going wrong, and then those breakpoints made me understand that the method was more bad than I thought. And that also made me come to the conclusion that I need to make this test as well. Because I decided maybe if size 0 doesn't work, how do I know size 1 is going to work? Right? Don't know. So that's how I came up with this method. Now this method does the same thing as before. It just adds one item to the list before it removes it. It checks if the size is 0. Perfect, right? That works just fine. I'll just hover over that for a second for you guys there. And then I used breakpoints to figure out what was going wrong, and I made my code pass my own test. Now I've got a bit more of a robust linked list, and this is the exact kind of error that you guys might not have in the mini tester, but might have in your assignment tester. This exact kind of thing, where you're testing for these base cases. You may or may not have it in mini tester, but I can be pretty sure it's going to be in the real tester, this kind of stuff. And that's why you want to test for it. So we have 0 now, and we have 1. Can you guys think of any other number we might want to test? Well, how about we could test the case of n numbers? Let's just say we want to test any number greater than 1. All of those other cases. Do those work properly? Well, why don't we try writing that? Because remember, we have our generator for strings, so we can say now private static boolean test remove from size n. And now we'll say int or intensity. And this will test it removing from a list of a length that we come up with. So I'm going to copy paste the same code, except now I'm going to say this.size is equal to intensity minus 1. And then here I'm going to say fill list number of things intensity. And I'm going to say list remove last. And now this method is testing for n things. It's testing removing an arbitrary number of stuff. So now I can say plus remove from size n, and we can make size n like 35. And just to make this a really good method, we'll say if intensity equals 0, return, or what's it called again? Test remove from size from empty, and we'll not even do 0. We'll do if intensity is less than or equal to 0. And now we'll say that. Okay, so now test from size n is our method, and now we can let's see if it works well for a size 35, right? All right, true, true, false. Okay, so it doesn't like the size 35 list. All right, let's see what's going on with this. We'll see that we're removing this. Oh, that's why the list should not be empty. Okay, it was a problem in my tester. It was not a problem in the code. Now we can rerun this, make it work properly. And now it returns true, true, true. But let's say we want to be super sure. We just want to really grind our code and make sure that there's no chance in hell it's going to break. What we could do is we could say for int I equals 0. Let's say I is less than 444 I plus plus. And we can put whatever number we want for I. We can say test remove from size. So if test remove from size n I system.out.println test failed to remove at size. And now this way, it's going to run through this loop, right? It's not going to tell us anything if it passes. But now if it's going to fail at any number I between 0 and let's just say this huge, huge number, it's going to tell us that it failed. And this way we're testing our code for when it's in really strange situations. This will in fact actually run through all these cases. We don't even need this anymore because we're already testing 0 in this test remove from size n, and we're already testing 1. We're testing all the numbers. I'll just add another case here to make it a really good method to say else if intensity is 1, return test remove from size 1. Okay, so now if we run this, it's going to take a while before it gets to that. Oh, and look, it's already starting to fail. Our linked list is bad for really, really, really big numbers, I think. When does it start failing? Oh, actually, no. It's because of this. It's actually passing every big number. And I forgot to put an exclamation mark. You can see that that is a common mistake. But now if you're running it, and we test it, it's going to go a really long time. It's currently, using my entire computer to test this bloody linked list. If I open my task manager, you can see that it's using like an entire processing core for this. It's like a lot of usage. And eventually, it's going to run through all the numbers. I should probably have not put such a big number, but I'm really trying to stress test it. I'm trying to like burn this algorithm to make sure that it's not going to break. And then eventually, after it finishes running through all these numbers, we can be damn sure that this method is rock solid. Like, there's no amount of things they can remove from the end of our list, no matter how big our list is, to break our list. There's nothing they could remove that's going to be, that's going to break it. Except, of course, we're not testing for null and stuff. If we want to make it really spicy, we can throw in some spice, and we can say here, in our fill list method, we could also put in, like, some chance. We can say, like, if... I'll use randomizing for this. So I'll say rand equals new random. And that's how you create random numbers. I could say, like if rand.next int 100 is divisible by 3. We're going to make it null. So we're going to say list.add null. And now we're going to say else list.add test I. Now this way we're making it a little bit more spicy by adding, let's just say next int 5 I. Alright. So now we're making it like really spicy because we're varying up what we're putting in the list. We're also throwing null into the list sometimes. Let's see if that breaks it. What is ran.nextIntBound? Oh, I really should explain that, shouldn't I? Well, ran.nextIntBound means it's generating a random number with a maximum size of the bound. I should probably actually introduce you guys to random properly, but let me just explain the spicy fill list first. So what the point of spicy fill list, actually I should probably say, like, you know, this makes it spicy. What the spicy thing does is it randomly adds a null to it at a certain percentage of the time. So for some portion of the time, it's going to throw in nulls randomly to this tester, and we're going to see if that's going to break our code. And we can see that because we're running through this like really huge number of tests, and it's not failed yet, it's probably solid. I'll make this number of tests smaller, just so that it doesn't break. And there's that. So it didn't fail any tests that are like under size 1500. All right, time to explain to you guys the randomizer. The randomizer is our best friend for debugging because it stops us from having to come up with our own test cases. The randomizer lets us generate data to test with. So here you can see that I am generating this string based on random, and I'm also using random for a chance. The way I do this is I create an object of type random. Here it's random rand equals new random. In fact, I could just do a bit of a test of random right up here. I can say, in our main method, I could say, random rand is equal to new random. And if we want to make it repeatable, we can put a seed in here. So if we want to be able to repeat the same test multiple times, we can put our seed in here, which can be any number. If you've ever played Minecraft and you're generating a world, it's using this, and it's putting a seed in there, which means it'll create something of a certain type, and it'll use certain information to create it. Random number generators in Java are not really random. They're just using some math equation to like really distort the heck out of your number. So the seed is just what you throw in there to start it off with. Right now I'm going to do a seedless random. I'm just going to say system.out.println seed is, so that if we see some errors, we can replicate them. Oh no, we can't get the seed. Oops. All right, well. Do you have random imported and like set up like this? Did you create a random object first? Like you have to do this first. You have to say random rand equals new random, which is a type of object, and then you can you can generate it. Yeah. Interesting. What does it say? Huh, that's interesting. So is what you're writing exactly the same as what I wrote in here? I'll send my fill list into the chat. There you go. And we'll see if that works for you. That's just the contents of the fill list method. But here, I'll explain random. So here I'm creating a new random. I'm going to set the seed to this, the system time. And I'm going to say system.out.println seed is, or let's say seed. And now we have a random number generator, which is like generating random numbers, and we know how to repeat it. Like we know how to make it repeatable. So now we can say, like, let's make a game out of it. Let's just say, guess the number between 1 and 3. Okay, I'll go over seed again and the difference in a sec. I'll just make the game first. Okay, so let's just say system.out.println. We are playing a betting game. Guess a number between 1 and 3. And now we'll say int number is equal to rand.nextInt with a bound of 2 plus 1, which will, so this generates, rand gives a random number between 0 and 2. We add 1 to make that 1 and 3, right? And now we can say scanner s equals new scanner. That's just to make the person be able to input. Right, we'll create a new scanner. We'll import that as well. And now we can say if s.nextInt equals the number system.out.println you win, else out.println you fail. Number was plus number. Right, so now we can see that we have a game out of this where we can try to guess the same number as the computer. So now it's saying the seed is this weird ass number. Guess a number between 1 and 3. I'm going to say 1. I win. Okay, so the number was 1. Now if we run this again, are we going to get the same result or are we not going to get the same result? Let's see. So if I run it again, there's a different seed, and now if I guess 1 again, I fail. The number was 2. So what if I want to recreate the situation where I won? Well, for that I can use the seed. Instead of saying the seed is system nanotime, like I've copy-pasted the seed from the time I won, and I can paste that number in here. Now if I run it again, I can guarantee that if I put 1 as my guess, I'm going to win, because the seed is what dictates how random works. What the random class does is it generates a random number based on a mathematical equation, which really distorts the number you give it. So I'll give it an input of this seed, like 1, 3, 4, whatever. And it's going to distort that seed to high hell. It's going to, like, you know, put it through some crazy equations that are going to make it seem completely random. And then that's what gives me my number generator. And they use that number generator to generate things like ints and everything like that. So yeah, using the seed, I am able to, generate, this game. So if you want to make this game and, like, you know, maybe make your friends lose some bets, what you could do is you can, let's say you can keep the seed as system.nanotime, which is just a source of random information. When you're generating random things in computer science, you want to generate based on some physical thing you can't predict, just so that it's actually random. So now the seed is this. Now we can see the seed is this number. If you want to make a bet with your friends, you can say, okay, I can guarantee that I'm going to get the same result again in this completely random game. And all I need to do is change one tiny bit of the code. So let's just say I guess 2, I win. Let's say I want to win again. Well, then I can put the seed into here, and I can guarantee that I will always win if I use the number 2. That's how the whole random thing works. I'm going to copy paste our random game into the chat. Yep. I'll maybe even make a separate class for it, just so the people who are looking at this later can have an easier time understanding it. I'm going to call it random game, and I'm going to have a public static void main string args. Right, and now I can go back into my tester. I don't want the random game here. I want it in here. All right, so I'll send you guys the full code for the random game as well to the chat. That will be right here. There's the full code for the random game class. You can play around with that. That's just to explain to you how random works. And I think I have got an extraneous close bracket. No, I have not enough close brackets. I'll send it properly. So there's the random game. But that's not what we're going for here. What we're trying to explain is that we can use this randomizer. So the seed makes rand return a predictable number. Yeah, that's exactly. So seed is what dictates how the random generates numbers. So if you have an error that comes up and you've randomized all of your information, the way you can recreate that error to debug it is you can take note of the seed and then set the seed to that so that you can keep repeatedly seeing the same error again, make it do the exact same thing again. That's the point of rand. The way I like to run my testers is I like to make everything random, right? Like notice how here, instead of manually writing the tests to make them run, one by one, I've done this for loop, which runs the test 1,500 times for me. And it does it randomly each time. Like it does a randomized test each time between 0 and 1,500 times, right? And this test that is doing it randomly, if it ever fails, the only way I could ever see if it fails or not is if I know the seed. Because if I have no information about what it's being randomized from, and it just fails sometimes, that I won't be able to debug that. But if I know the seed, I can recreate the situation and I can debug if it has an error. But I'm pretty sure this test remove is very solid because it's not failing for any number between 0 and 1,500, and it has a data set that's partially null. So we know that it's probably pretty solid. And hey, while we've done all this, we've had enough time to be able to make my a nice, pretty runtime efficiency tester open, and I can show you guys a bit of runtime efficiency stuff now. And that will bring us into testing runtime efficiency. So if I open on my main screen, let me just switch over to that, move my chat over so I don't broadcast you guys, don't dox you guys here, and show you guys the correct screen. That's real DT, and I'll transition that over. Give me a sec. I can show you this, which is my old runtime efficiency tester from last year. So if I run it, it's going to graph how fast different methods run. And that'll let me explain how to test runtime efficiency. So it's just taking a second to open. You can see it's making a graph. I'm going to compare merge sort and bubble sort. And you're going to watch bubble sort get destroyed. So the yellow curve is bubble sort. The orange one is merge sort. You can see merge sort is a lot better than bubble sort. Wow, big news. Well, the important part is the axes of this graph. Here we've got the runtime in nanoseconds on the y-axis. And on the x-axis, we've got the number of stuff that we're putting into our data set. Right? That's clear with everybody? This is the number of things in our list, and this is the amount of time it takes. Number of things in our list, amount of time it takes. Those are what we plot our big O notation runtime efficiency graphs on. This is what it means to be O of n squared, or O of n factorial, or O of n whatever. That means that this curve here is roughly following y equals x squared. This one looks more to me like maybe y is equal to 0.8 x squared, something like that. But it's equal to an exponential curve, right? You can kind of see that. You can watch the trend. It's a bit exponential. Compared to the n log n curve down here, it's night and day, the difference, right? And that's what we're really testing. So now, does anybody have any clue how we could go about generating data like this from our thing? We did it just before, but can any of you maybe make the connection of how we can generate how long it takes to run with an increasingly large data set if we've just built the tool that lets us create an increasingly large data set? Yeah, that's right. That's exactly what we should use. So if I transition us back to the other IntelliJ here, and I open that up again, we can see that here we already have our tools, which we use in order to generate an arbitrarily large amount of data. It's called fill list. So we can already make lists of an arbitrarily big size. And we can already get our runtime, just like we did. The only difference between this output and the graph is that the graph is pretty. That's like literally it. If you put this into like Google Sheets or Excel, you could even get the same graph out of it, like if you wanted to. If you wanted to be very practical about it, you could just copy paste these numbers into a spreadsheet and then graph it. Or you could, if you wanted to be fancy, you could make this output as like a spreadsheet file, or if you want to be even fancier, you could make like a graphical tool like I did. But either way you do it, you can see how, well, this method, right now we're testing the runtime efficiency of filling the list. Well, filling the list is taking, here it takes 900 seconds, or 900 nanoseconds, 1600, 3500. It's going up, and it's going up pretty fast. So I want to say that it is not fast at all. And I think that would be pretty accurate, right? Because the way we're doing it in our list of links when we add something is we're traversing our list, we're moving through it, and we are adding it to the last node. So we're doing get last node, which does a while loop to traverse our whole list, and we're adding it to the end of the list. And that's really slow, right? You guys can see why that would be slow. So that is what we're testing for here. We're testing for how the speed of running the algorithm changes as our data set increases. My webcam is currently being a little bit annoying, so excuse the black screen there. I'll try to restore that. But while I try to restore that, does anybody have any questions about how the heck we're testing this and what it's doing? Oh. No, it doesn't like that. It doesn't like my webcam. Ooh. Oh, whatever. Oh, no, it's back. All right, so I guess it's all clear to everybody. I have a question on the other file. Why do you use mod 3? I use mod 3 just because I want it to have like a certain probability of being null, and you can do whatever you want for that probability. You could do like, let's say it would be equal to the probability of the next int between 1 and 3 being equal to 3. Well, I guess that's never going to happen in IntelliJ. So 2. Right? And this would be a 1/3 probability. You can do whatever you want for this. I just decided that to be like a fancy way to say that we can have whatever expression we want. This is just saying that if the next random number between 0 and 2 is 2, so that's a 1/3 chance. Does that make sense? Like it's just a matter of chance. If we want a certain proportion of our data to be null, but we don't want to know exactly when it's going to be null, we can do this kind of randomizer system, where let's say we want it to be a 1 in 10 chance. We can say if the next number between 1 and 10 is 2, so that's a 10% chance. If we want it to be let's say, out of 1,000, we can say 1 in every 1,000 here, roughly, is going to be null. Of course, it's random, so we can't be sure. In some situations, they might all be null, or they may none of them be null, but usually we expect 1 in 1,000 of them to be null. Does that make sense? Like it's a matter of probabilities and like how often we want it to be null. And this is only a matter of like however you feel, like whatever you vibe with. I usually keep the null factor somewhere like 1 in 20, something like that. Because you don't want it like every time, but you want it to be like a rare little treat for your program to make sure it doesn't break. I'll do 1 in 50 here. So that's that part. And now if I go back to the speed tester, yeah, what I'm saying is we're testing how fast each method works as you increase the data set size. So we can see that adding is pretty slow because it has to traverse the entire linked list. Let's try comparing adding to something that should work roughly the same speed no matter how big the list is. For that, I'm going to say maybe something like, let's look through our methods. Let's find one that's going to work in O of 1. Getting the head should return O of 1. Yeah, we could try that. Get first node, is that one of these? I'll look to my structure. I'll just make sure. We might not have any O of 1 methods. We totally should though. ToString, remove last last node, get node. Okay, well we're gonna say get first, right? That's gonna work hopefully at the same speed no matter how big the list is because it's O of 1. And ooh, my webcam is totally messed up. Nice. Okay, well we're gonna enjoy the extreme stretched close-up of my face because my HDMI cable is bad. Oh no, we're not. Okay, whatever. Here, let's compare this to a method that is O of 1. In list of linked tester. So instead of just finishing there, we're also going to say print line times end time. Now we're going to say long start time 2 is equal to system dot nanotime fill, or now instead of fill list, we're going to say or tested dot get first. What did I say? Oh no. Oh, whatever. Don't care, because that's an inner class that was annoying. Now long end time 2 is equal to system dot nanotime, right? And now we can say, end time. Okay, so now we're gonna see these things side by side, and I'm gonna make these into. Yeah, this will all be published on the GitHub after it's done on my courses, and it'll be updated on the GitHub on the solution branch. So here we can see side by side how fast each method is taking to run. There's one that just should be O of 1, and there's one that should be O of n, I think. Right? And now we can actually see side by side. This one is fluctuating, get head. It's starting at 7,200, it's going between 100 and 200. And it's going up a little bit, but it's also going back down. Like it's just spiking. The curve is kind of looks like it's relatively flat with a few waves, right? Which is exactly what we expect from O of 1. Whereas this one is just skyrocketing up. So here we can see side by side what O of n, let's say, it should be O of n by my logic, but it might be something worse just because it's bad. And O of 1 side by side could look like. And if we want it to be really clear, we could say like slow 1, comma, probably O of n. And here we could say plus fast 1, O of 1. And now we can see side by side how those look. And now we can see that the slow one, O of n, is very, very slow indeed. And the O of 1 is very, very fast indeed. Does that kind of make sense to everybody? Maybe makes big O notation make a little bit more sense. how it's increasing as we increase the size of the number of stuff in the list. It takes longer and longer, whereas the fast one takes about the same amount of time, no matter how big your data set is. And remember, the way we're testing this is we are putting a timer, or we're checking what time it is at the very start, the millisecond we call, or I guess the nanosecond we call the next method. Then, as soon as the method is finished calling, the line like right after the next line, we test what time it is again. We found how long it took. Then we do the same thing again with the O of 1 method, and then we just print out the difference. That's all we do. Now, if we go back to my other monitor and we look at the current, or like the graph thing we're doing. Does everybody see the graph? How did you get these numbers on a graph? Do you use a plugin? No, this is some code I wrote myself last semester, and I'll be trying to make sure to get your hands on this, but I'm not completely sure if I'll be allowed to. I'm working on it. You guys should be able to maybe use something like this later on in the course. But yeah, this is my own tool. It's not something you can find a plugin for yet. So here we've got number of stuff in the table and how long it took. Here we can see that it's taking quite a long time to do bubble sort, whereas it's taking very little time to do merge sort. And this is the exact same stuff we were seeing before in the console. Like I stressed that this is using the exact same technique. This is just so we can visualize what it means to be O of n squared or O of 1 or whatever. Here we can see n log n is so much faster than n squared. That's about that. That's what it looks like to be n squared. That's that. And if we transition back to where we were before, we can see reflected in this print line the very same idea, the very same concept is being shown. Here, the numbers are getting real big, real fast, and here the numbers are staying right down there at the floor. These numbers are so big that if you graph both, these ones will basically be a dot on the floor. They're going to be so small. And that's what we're looking for when we're comparing runtime efficiency. Now, a great way to test runtime efficiency for you guys in Comp 250 is to test it compared to Java's built-in methods. Because everything you do in Comp 250 is something that's probably been done before. We're not inventing new algorithms. And Java usually has these algorithms built in. So here I'll show you what a good technique could be. See, here we've got the built-in Java merge sort, and we've got a student implementation of a similar sorting algorithm. You can see they're relatively close in speed. The Java one is still a lot faster because the Java one is able to use some things we haven't learned in this class. Like the Java one uses a lot of tricks and shortcuts. And the student one's probably quite imperfect. It's not like a very good implementation. But you can see here, the comparison is important. Now this one is still one that scored well last semester. This one is one that still got like full marks, even though it's a lot slower than the Java one. But it gives you an idea of the ballpark speed if you compare it to Java's built-in methods. And again, I'm testing this using the exact same technique as before. There will be a lot more videos going in depth into this kind of testing. I'll even try to release this tool for you guys, but that I can't guarantee. And yeah, we'll make sure that you have access to this kind of testing in some form. They're the same O notation because one probably has a big constant. Actually, I can't even guarantee there's the same big O because big O notation can't actually be mathematically calculated using, or it can be computationally calculated. It can be mathematically calculated, and that's something you'll go into in like Comp 251, Math 240. You can calculate that kind of stuff theoretically. But in practice, because computers are running so many other things and because there's no way to make it do anything except by approximating, like you can do curve fitting and approximate which big O notation it is, but that's not very precise and you need colossal data sets. So you're basically just getting the vibe from it with your computer. Like you can see if it's going exponentially up a lot faster, you can see it's probably pretty good. Like if I look at this fast sort implementation and I compare it to something really slow like bubble sort, you can see that the fast sort is, well, it's substantially faster. Here it looks slower, but if we turn on turbo mode and we make it go like really fast into huge data sets, we can clearly see that bubble sort will take a lot longer. Here we can already see this is the fast sorting algorithm. This is bubble sort. Bubble sort is much slower, and that's kind of what we're comparing to. If we compare it to the array list merge sort, you can see that both array list merge sort and this student sorting algorithm are increasing at roughly the same rate. The student one is worse, but you can see the student one isn't like taking off into space, whereas bubble sort is. That's how we usually compare big O notations. It's not by the minute differences between things. We're just kind of reading the vibe. We're saying, the really slow O of n squared sorting algorithm is just going to space. It's like ridiculously slow. It's literally an exponential curve. And then our fast sorting algorithms are like little lines on the floor compared to it. And that's what we care about. If we compare it to something that's like O of n, so we can say like, this one is O of n, we can see that the O of n one is also substantially slower. You can see it deviating from our two sorting algorithms quite a bit. And that's generally how we test. And again, we don't have to use this fancy graphical tool for that. We can also use a simple print line to accomplish the very same thing. Here, all I'm doing is this code. I'm measuring the start time, filling the list with an increasingly sized data set, measuring the end time, and then printing it out. And that's accomplishing the very same thing. If you want to be fancy, plot this in Excel, you've got a graph. And you can even do some curve fitting. And if you do curve fitting in Excel or whatever program you want using some linear algebra, you could also get the actual, O of n expression for it. Like you could do it. You just need to run it for a long time, get like a really big data set and maybe like a few million, and then you're good to go if your code doesn't break in a few million. Hopefully that makes sense. Again, today we went over the debugging technique of doing a sweeping test, which tests the base case, so 0, another base case 1, and then runs through everything. We then used this debug to fix our list of links class and make sure that this method, remove last, isn't so bad anymore. So this one got fixed in the process of our tutorial. This one was bad before, now it's not bad anymore. And we discovered this by running a tester. And we could do this kind of tester for every method in our linked list. We can make this tester really good. With this tester done, I can be pretty confident that remove last works. We can see also that remove last is working in the runtime efficiency of roughly O of n, probably. And it's much slower than O of 1, but it's much faster than something like bubble sort. And, well, that's kind of our idea of it. If you want to be really sure about everything, again, you can graph it, but should be good to go. Anybody have any questions? And also an FYI that I am posting a lot of these short video clips on my courses and Piazza. You should be able to see on the latest announcement that there have been like a series of 5, I think so far, videos on these sort of topics, and I'll continue to post those. So if any of you guys have suggestions for future short video content, let me know. I'm happy to make them. Anything you want explained in something like a short video or an animation, I'll do those. That's kind of sort of edging out and replacing FAQ because nobody came to FAQ. So, yes. Stack and queue? Actually, okay, you know what? It's 5 p.m. I'm going to go over a little bit overtime for you guys if you don't mind. And I'm just going to tell you about stack and queue because in real life, they're the easiest things in the world. A stack and queue is a linked list, usually a doubly linked list because you want to be able to push and pop from either side. But if you want this to be a really bad stack, all we have to do is change, like we can create a method here. We can say it like public epop, right? And then we can say return, or we can say, let's say, list or e data is equal to get last, and now we can say remove last, and now we can say return data. There, that's a pop method. This is a bad pop method because it works in O of n. You should make a doubly linked list and just return the head from the back, like you return, I guess, the butt of the list, whatever you call the head on the other side. That's a pop method. Peek is just you don't remove it. That's peek. And then, yeah, for queue and stack, the methods are really simple. Queue and stack are just linked lists. That's all it is. Nothing special about it, nothing fancy. A queue and a stack are just a fancy name for a linked list. E is a generic type. You'll be seeing E in your, well, E is a standard generic type. Here I did a list of links with a E as the generic type. You might see some other letter here. E is just the standard. That's what's used a lot of the time in Java. You'll have to learn this for assignment 2. And if you go back to tutorial 3, you'll see me implementing this linked list and explaining the generics. And I can do another video on generics if it's not clear from that as well. Does that kind of, what? This is not a good one. This is a slow and bad. Bad. You should use doubly. Better, you can make a doubly linked list, which is a list which keeps track of its start and its end. Because the thing about stacks and queues is sometimes with a stack or a queue, you want to put something on the top of the list, right? Like it's first in, well, there's first in, first out, and there's last in, first out. Depending on which one you're implementing, you may need to say add something to the top of the add something to the top and pick up something from the bottom. So like in a queue, you add something to the top, you pick up from the bottom. It has to be doubly linked because you want both of those to work in O of n, right? You want to be able to add something to the top and make that take O of 1. You want to put something on the bottom, you want that to be O of 1. So you have to have access to the first and the last node in O of 1, which means you have to keep them as fields. So you have to make a doubly linked list. I mean, there's other ways to do it. You could also track your last node, but I feel like that's a bit of a roundabout solution compared to just making a doubly linked list. So yeah, again, doubly linked list, probably how you want to implement that so that you can do O of 1, pop and push and peek and all that. And in queue and DQ, all of those could be O of 1. But again, yep. Again, yeah, go ahead, sorry. Yep. Wait, do you want which method to return an O of 1? Can you repeat, sorry? Mean of the elements in the stack in O of 1. That means you could keep track of the mean over time. Like, okay, so I don't know the assignment super well. I haven't looked at it in detail yet. But what I could tell you now is that if you need to keep track of something like that, O of 1 basically means you have to be returning a field. If you have to do some logic like a while loop or a for loop, it's not going to happen in O of 1. So usually what O of 1 means is you have to keep track of this elsewhere, outside of your O of 1 method. Or like, yeah, and then you should just return a field. That's usually what O of 1 is. Or like return something from the index of an array. Yeah. No, it's not. If you call an O of n method, it's going to be O of n. It's going to take the slowest speed. But what you could do is, remember, when you're adding stuff and when you're removing stuff, you already know the size, and if you already keep track of the mean, you could probably find a solution to keep track of it. I don't want to go like too in depth because I don't want to give out the solution, but I could say that consider when you're doing this logic. Is it possible for you to come up with a time when you can do this, which will not cut into your runtime of that method? What I mean is, when do you want to do the thinking? Do you want to do the thinking about what the mean is when you ask for the mean, or do you want to have it prepared for when somebody asks? Because think about when the mean changes. The mean is going to change when the number of stuff in the list changes, right? So you have two options. You could calculate the mean when you're asking for the mean, or you could calculate the mean when the number of stuff in the list changes. So if you think about that, I don't necessarily want to go into more detail than that because I don't want to completely give it away, but I'll say that, think about when the list changes, and maybe you want to calculate the mean when there's a change. Of course. Is there any more questions? All right, I think that should be good for questions. If you have any more, feel free to reach out. Next tutorial's on Monday. Probably going to be covering more stuff on terms of runtime efficiency, maybe queue and stack. We'll see. Whatever you guys feel like you're struggling with for the assignment, let me know. We can cover it. And there will be more short videos on various topics gradually coming out on my courses. Good luck, guys. Hope it all goes well. Tutorial 3 is how to implement a generic linked list. So if you want to see some code, that's where you go. All right. See you guys later. Thanks for coming. Enjoy.